Okay, hi, I'm Ryan Alexander. I'm a fourth-year PhD student at the University of Hull, working with my supervisors, Fiona and Vincenzo. And I'm going to be talking about the work which I've been doing for the past year, trying to constrain the Type Ia progenitors to their chemical abundances. I think this first slide is a little bit, maybe a bit trivial for this audience, but these Type Ia Supernovae are the thermonuclear explosion of these carbon oxygen white dwarfs, which comes through either these two scenarios, the double degenerate or the single degenerate. The double degenerate comes through the binary of these two carbon oxygen white dwarfs, whereas the single degenerate comes from carbon oxygen white dwarf along with its companion helium-rich star. One of the discrepancies among these Type Ia explosions are whether or not they explode as sub-Chandrasekhar or Chandrasekhar, where the sub-Chandrasekhar is anything below 1.4 solar masses, and Chandrasekhar is approximately 1.4. Each channel can have either a double detonation, so a detonation of the helium core, for example, from the accretion of a helium star onto the carbon oxygen white dwarf, which will trigger the carbon explosion at the core, or the death relating to detonation, which happens at the Chandrasekhar mass, which is just the explosion of just the carbon in the core. The discrepancies which comes from these progenitors have been sort of discussed throughout literature, where Kobayashi 2020 suggests that up to approximately 25% of the solar chemical abundances comes from the sub-Chandrasekhar, whereas Dwarf suggests that the sculpted dwarf chemical abundances are best described at approximately 80%. Like a mixture of both of them, which is what we aim to investigate. We use IGTOL, the chemical evolution model. What happens here is that it takes place within a three-dimensional box of coordinates x, y, and z. The box is filled with primordial gas of hydrogen and helium, and from that gas, we start to form these stars. Each dot, which we see here, is an individual star, where the higher mass stars are denoted by the bigger point. So you can see that, maybe you can see it up here, these massive stars, which have much shorter lifetime, so blink in and out of existence here on the left. On the right here is our supernova explosions for core collapse and Type Ias, where we sort of see these supernova bubbles which occurs, and on the edges or the boundaries of the bubbles where gas sort of disperse, the chemical balances of the gases sort of disperse, and then later on, when stars are formed within this gas, they'll inherit the chemical balances of its predecessor. And that's what happens for 13.8 billion years in the simulation, until you get to the end and you can see the chemical abundance patterns along the galaxies. In our work, we create three models, one ultrafaint dwarf and two dwarf models. Dwarf A will mimic a shorter but more powerful burst of star formation, whereas dwarf B is a much more longer, much more shallow star formation. We have the volume of the boxes, where ultrafaint dwarfs is a little bit smaller than the dwarf. The infill gas is a lot bit bigger for dwarf models, as they are much bigger galaxies. We have the star formation efficiencies here, where it's not which is pretty low for ultrafaint dwarfs, so pretty high, much higher for the dwarf worlds. And then you have the maximum accretion time. So this is the time where you sort of have the maximum accretion of this infill gas. And from the models, from using IGTOL, we can get some of the stellar properties. So the number of stars, you sort of see here for each of the three models, the stellar mass approximated as we run the model 10 times, so we get 10 different averages and then sort of average out. And then you have the star major histories, which we try to mimic as well. I want to sort of the more parameters of the actual models. For massive stars, we use Kobayashi 2006 yields, and AGB we use Backus 2010. We use the Larson 1974 stellar lifetime equations, the Cooper 2001 IMF, and for the Type Ias, we use the Mausinger 2017 DDT equations with the minimum delay time as 150 megayears, which essentially means that 150 megayears after the star formation is where you start to see these Type Ia supernova events occur. with a normalization of about 10 to the 3 Type Ia per solar mass. So talking a little about the chemical abundances of the observations which we choose. So as we are focusing on these Type Ias, we choose to use nickel and manganese, as we found that those were more affected by these Type Ias than any of the other elements which we sort of have. So we have nickel to magnesium on the left, and on the bottom, manganese to magnesium, or as a function of iron. And we sort of look at these chemical abundances and sort of trying to track the patterns of them. So for manganese and over magnesium as a function of iron, so sort of on the left, we can sort of see on this violin plot that has a much more metallicity dependence than nickel, for example, which looks very constant over all metallicities. So this is sort of one of the sort of big conclusions or sort of factors which comes into our analysis later on. For our ultrafine dwarf model, we use the Kobayashi 2020 and the Keegan's 2023 Type Ia yields, where we sort of see the different progenitors as different colors. So in the blue, we have the sub-Chandrasekhar, and the green is the blue is the Chandrasekhar, the green is the sub-Chandrasekhar, and then the oranges is just the ultrafine dwarf observations, which we actually saw from the previous slide. So what we actually find is that the Chandrasekhar produces a lot more of these iron peak elements for nickel and manganese for Keegan's than is for Kobayashi. However, they're very similar for iron, which we thought was pretty interesting. Mainly because when we compare the yields for both Kobayashi and Keegan's, the nickel and manganese are very different from each other, but the iron are very consistent, which is sort of confirmed with our models here. One of the things we actually did as well, we conducted a KS test, which looks at the statistics for the observations and the model. So all we're seeing here, all these numbers that we're denoting here, is the maximum differences between the two cumulative distributions for our model and our observations. Where the lower the statistic, the more likely that the model and observations are from the same distribution. So the lower the number, the better the model, essentially. Where we actually see that for the ultrafine dwarfs, they're relatively similar throughout all progenitors, which we can sort of see here in our chemical abundances, that the Chandrasekhar actually reproduces a lot of the chemical abundances, excluding some errors on the top. Whereas the sub-Chandrasekhar seems to be very flat along sort of here in the green, which we can also confirm from the yields for both Kobayashi and Keegan's Type Ia models. I don't know how much time left, but this is the final slide. So finally, we have our doctoral models for both Kobayashi and Keegan's, where in the red we have the Chandrasekhar yields and the black is a sub-Chandrasekhar. We actually see that with only Chandrasekhar yield, we can actually reproduce a lot of the chemical abundances for both our observations. So we choose Sculptor for our doctoral A because it mimics similar star formation histories, similar to Leo 1, which is sort of the reason why we chose that for our doctoral B model. We actually see, interestingly, you can sort of reproduce a lot of the chemical abundances here, for example, in sort of this higher regions, only with the Chandrasekhar mass rather than the sub-Chandrasekhar mass, which is what a lot of the literature is sort of suggesting that for Josh models, a lot of the chemical abundances were sort of dominant for the sub-Chandrasekhar progenitors. Whereas what we find is that we can reproduce a lot of chemical abundances with only Chandrasekhar mass progenitors, which is sort of very interesting to sort of see that with our models and with our yields, which are very different with each other, you can get very similar results between Keegan's and Kobayashi. So, conclusions: the Chandrasekhar progenitors produce much more high abundances of nickel and manganese than sub-Chandrasekhar. There are higher metallicity dependence for manganese than for nickel. We actually use a 25 solar mass upper mass limit for the Milky supernovae, which we found in our analysis to be a lot more agreeable than using, say, a 40 or 100 solar mass upper limit for our collapses. And finally, our doctoral models can reproduce the chemical abundances for our dwarf models and ultrafaint dwarf models for Type Ia yields with only a Chandrasekhar progenitor mass yield. Thank you very much.